because that had a capacitor and the resistor were in parallel, and the inductor was in series with that?
I believe so.
So in this case, we had power supply, capacitor, and then it splits resistor and inductor. I think that was the master set. All right, epsilon sub naught, we know from the initial information. Is that 250 volts?
Yeah.
Okay, so we know what epsilon naught is. I know that VL equals VR. I know that V is equal to IL XL. VR is equal to IR R. So we can come up with a relationship between the two currents there. Because there's enough information to find XL and enough information to find, well, R is given. I know that IL squared plus IR squared is equal to IC squared. Now, is there a question about how we know this?
Yes.
Okay. It goes to the phasor diagram. All right, so we start out with VR, which is equal to VL, which I'll just call VRL, or I'll flip back and forth between those. I know the current is in phase. IR is there. I know that IL, for an inductor, the voltage leads the current. So there's my voltage, and it's spinning around clockwise, so my current for IL needs to be this way. That is a 90-degree angle. I know that whatever's coming across the current will split, so the sum of these two must equal that. Just from a Kirchhoff's junction rule. Except when I'm adding phasors, I add them like vectors. So that's IR, and so IC would be that. So IR squared plus IL squared is IC squared. From this, I know the relationship between IL and IR. So I can have either IL equals something times IR, or times R, or IR is, no, I said it right the first time. IL is something times IR, or IR is something times IL, either one. I can substitute into here, and I now have a relationship between IC and IR, or IC and IL. Back to the equation that I erased, where we had epsilon naught squared is equal to VR squared plus VC squared minus 2 VR VC cosine of theta. This is equal to, I know what that number is. That was calculated earlier on. This is I R times R squared. This is IC times XC squared minus 2 IRR times IC XC times the cosine of theta. I have a relationship between IC and IR, which I'll talk about over there. And so I can do that substitution in here. I know my R's, I know my XC's, I know epsilon sub naught. Potentially I should know theta at that point. And so I'm down to, the only thing I don't know is my one variable IC or IR, whichever one, or IL potentially.
Okay. once you have that, how do you find voltage across?
Alright, once I know the current going across, well, once I figure out either IR or IC, because I made another substitution, got it down to one unknown. Once I know IC, well, I know VC is equal to IC XC. The capacitive reactance would have already been calculated. IC you just found. You now have the amplitude of the voltage across the capacitor.
Okay.
And from these relationships, you have a relationship between IC and IR or IC and IL. So you solve for whichever one, because we know what IC is. Then we'll have the amplitude of the current for IR or IL. Then you solve for the other one. So you all have the amplitudes. Once I know the amplitudes, I can then find the amplitudes for the voltage, because VR is equal to the current across the resistor times the resistance. And the magnitude, the amplitude of across the inductor. Well, actually, you could go through this just to double check, but those two should be equal.
Yeah.
And all that's left is phases.
So, is it Kirchhoff's rules? Is it just adding them together to find the amplitude of the epsilon sum naught?
Oh, how do we get epsilon sum naught? That's given because I tell you in the problem the RMS value.
Wait. How do we find the angle of epsilon sum naught?
Oh, how do you find the angle?
Yes.
As in the phase of epsilon sum naught? Okay.
Well, I think here it's just angle.
I didn't have perfect wording. What?
I assumed what was going on is that this becomes where 0, phi is, and then we were finding the angles that we have to set them based on that because of assuming the voltage started at its maximum positive value.
Yeah, so when time is zero, so the voltage started at the maximum possible value. This is the voltage of the power supply. So, so when time is zero, you want cosine of zero, so the phase would be zero.
Okay. So then this becomes a phase shift to 0 and everything else is relative to that.
No, the power supply becomes a phase shift to zero.
Oh. Okay. And then everything else is relative to that.
Yes.
Okay.
So, does that answer your question?
Not about the angle of epsilon sum naught, but a different question.
Okay. All right. So, the angle of epsilon sum naught. All right. Because I have VR this way, and I have VC this way. Epsilon sum naught is there. If I know one of these angles, because that's VC, that's VR, looking at this triangle here. That's epsilon sum naught. That is not a 90-degree angle despite the way it's drawn. Or not necessarily. I know so all that other stuff I was doing was assuming we knew that angle there. And I just have to think through this every time. oh, we know at this point, we know that angle. Because this is 90 degrees behind the current for I sub C, which is the sum of IL and IR. Yeah, there's enough information to find that.
Yeah.
Okay, so you're good there. Okay. So we know this angle here. So if I sort of extend this from a geometry point of view, extend VC, I'm doing dotted line because VC is not pointing in that direction. I've got this by two parallel lines here. Parallel lines cut by transverse corresponding angles are congruent. So this angle here would be the same as this angle here, which would be pi minus whatever that is. So that's theta, which is pi minus whatever the phase difference is between R and C.
Okay.
Once I have this angle, and I'm trying to figure out where epsilon sub naught is, well, looking at this triangle, although I could just easily look at the other triangle, but looking at this triangle, epsilon sub naught, theta, if I can find that angle there, VC and VR, small f signs. So epsilon sub naught, which we know over the sine of theta, which we know is equal to, if I want that angle, VR over sine of phi. And at this point, we figured out VR. So you can find phi, and so epsilon sub naught is the angle phi in front of whatever VC is. So you take the phase shift of VC, add phi to it, and that's where epsilon sub naught is.
Okay.
And then you can just adjust everything to whatever initial conditions there are.
Professor Fox,
Yep.
can you tell me this is like a reasonable number for the dielectric constant?
Yeah, reasonable, I would expect the number to be more than 1 and less than 3.
Okay. Okay, thank you.
Sometimes people get 0.5, and those students, I assume, will get Nobel Prizes. I got a lot of students, based upon their results of labs, deserve Nobel Prizes.
Where's our Nobel Prize?
It's the joke that they cheated.
They just got crappy data.
Oh, okay.
Yeah, they got groundbreaking data.
Oh, yes, that's right, that's what I meant. Other questions?
I managed to go about computing everything, and my currents are like way off, and then my voltage is like off by like 9 volts.
9 out of how many?
Well, like the sum of VPS and VR after taking into account the time. The voltage with that of VC
Oh,
is off by like 9 volts. This is like step 5.
I did this one.
yeah, I would expect them to be closer to that.
Yeah.
They might have different.
And then my currents are further
Just
off.
for the same.
Yeah,
What did you do?
there's a mistake somewhere there.
Did you do the slope over?
I mean,
Not over the year?
it's like when you're taking a test also, you end up with something like that, now you're going, all right, how much time am I gonna spend trying to figure out
Mhm.
where potentially it's a negative sign in the wrong spot, or potentially
Yeah.
you typed into the calculator wrong, or there's some fundamental thing that you missed.
Yeah.
So, other questions?
I'm still very confused about the rocket ship thing, but I'm a working for FIL after.
Okay.
Work it out, so.
All right, let's move on to the next bit. It was that debate in my head of whether we do quantum next or whether I sort of do an old test. And I think I'm opting for an old test.
Yeah, I kinda like that.
And question of which old test to do. Ooh, I printed that and didn't pick it up. So what I'm gonna do is, why don't we take a break here? Let you finish whatever you're working on, and I'm just gonna let the camera roll. No, I am gonna pause it.
Oh, we can't make faces in it and stuff for the video.
You want to? I can let it
Now's
go.
the time, if you want us to.
I'm gonna pause it, and then if you want.
No.
All right, we're recording again.
Oh, I missed the whole story. I used physics to help my former high school with truck pull, because they were pulling up. So I was like, no, we wanna pull out this way, but we can maximize the horizontal component of our force.
Excellent. Physics has uses.
It does, man, I hope they win now.
What's it back here?
Same number as the distance from.
Okay, so I would like to talk to all of you.
Can I ask one,
Okay?
can we do one more of those, phasers? I'm getting a number, and I just wanna see if that's the correct one. So I have a phaser with 2.681 radians. And
This
then, oh, yeah, go ahead.
This is lab?
Yeah,
Okay. So 2.681,
radians, and then, a phaser with negative 2.9928 radians.
negative 2.998.
9928, yeah, so negative 2. And then I added the 2 pi to the negative,
Okay?
and then subtracted those two.
Yeah.
That's my difference, correct?
Most likely, yeah.
Okay, thanks.
And the reason I say most likely, one of the phasers should be leading the other one. So, assuming that this is the one that's supposed to be leading, then yes, what you did was absolutely right on. If this is the one that's supposed to be leading, then the difference would be huge.
Yeah, no, that's, the bottom one's supposed to be, wait. When you're saying leading, like closer, if you're going clockwise, closer to the origin?
Leading as in, it's spinning this way, this one would have the one that is supposed to get, I guess the leading one, the one that does, way of differentiating messes me up here. Like in this drawing right here, this is leading that, which is leading that. Because they're spinning clockwise, this is the lead one, the first, second, third place. That's what I mean by lead.
Is in the phasor diagram always spins,
Counterclockwise. Yes.
counterclockwise? Okay.
Because I assume the convention was set up before clocks were.
That makes sense. What did they call things before the clock, when they were going clockwise?
Okay, they just use. Use the right hand rule.
The second hand rotates inwards.
Oh, they're just a little more complex about it.
I really don't know. Probably there were so few people working on that kind of stuff at that point that,
Oh, they're probably just farmers and stuff.
no, it was probably, I mean, the people who were working on that was probably a very small percentage of the elite.
That's true.
The elite.
I feel, well, I mean, everyone was just trying to survive, right? So they were just worried about if the sun was up or if the sun was down.
All right, so,
Oh, yeah, they're going the other way.
oh, okay. Then that's potentially a discussion the two of us should have
Yeah.
instead of the whole class. All right, so this is the summer of the first summer of the pandemic. It was basically open note, open book, though I made problems harder than I would normally. At least some of them.
Nice.
All right, so we'll establish I hat, J hat, K hat are in the X, Y, and Z directions respectively. So right-handed coordinate system. All right, so what is the direction of the force on the object in the situations below? And so I have an electron traveling in the I hat direction. So I, J, K. So an electron traveling in the I hat direction into a B field, which is in the K hat direction. So I got B coming out at us. So what's the direction of the force on the electron? We can do right-hand rule, or we could do the math equation. Both get you the same answer.
The math equation, to be exact.
Force on the moving charge. Q V cross B.
This is a review for Monday.
Yeah, this is old test. This is the test from summer of 2020. So right-hand rule, I got an electron traveling that way. We can treat that like a positive part of going the other direction. So thumb points that way. And, wait, sorry, wrong one. No, actually, two right-hand rules. So I can treat it like a current flowing that way. It would create a magnetic field like this, which is supported on the bottom and degraded on top, because the magnetic field from the electron is going like that. So the electron can be forced up towards the weaker magnetic field.